Molecular modeling is a science which attempts to understand various biological and chemical phenomena in terms of the properties of these constituent atoms and molecules. It provides a link between the living world of the biology and inanimate world of chemistry and physics. Molecular modeling attempts to understand the structure and properties of atoms and molecules. These atoms and molecules are the basis of universal physical laws, and most often it has been used to predict the structure and properties of molecules, because the structure decides the function of the particular molecule. And all these things are explained by using various biological phenomena. Here you can see the molecular modeling. It can be broadly divided into two groups. One is classical mechanics, second one is quantum mechanics. In case of classical mechanics, you consider the atom, it's like a spherical ball, and the bond is like a spring. In case of quantum mechanics, consider the probability of the electron that is being at a certain place. That means the probability of finding an electron at a particular place, and you do not actually have an explicit, that means explicit means a clearly known position of either of these atoms or bonds or anything now. Quantum mechanical methods broadly classified into two types: empirical or semi-empirical and ab initio methods. The calculations of empirical methods based on crystal structure of the protein and crystal structure of molecules, but the calculations of semi-empirical methods, it involves a lot of parameterizations, that means finding a parametric equations. It is based on the experimental data. These parameters, on the other hand, it can utilize the parameters from ab initio methods, which are theoretically pure. In the sense, it requires a little help that is taken from experimental measurements. Finally, which method has to use? Should we use classical mechanics or should we use quantum mechanics? The answer lies in the computational power that we acquire. The classical methods are always simple and these are crude, unrefined, but they can apply to operate very large systems like your proteins, protein complexes, nucleic acids with hundreds and thousands of atoms. But a quantum methods require a lot of computational power. You can use this in semi-empirical methods where there is a little approximation for moderately large systems. That means with 100 or even 200 to 300 atoms. And coming to the ab initio methods. Ab initio methods are really extremely theoretically pure. This doesn't rely on any assumptions and it also requires high computational power. By this can be applied to only small systems with a few atoms, which may not be intense, and it is applied to even hundreds also. Let us talk about the second topic, coordinate system. The method in molecular modeling is to represent a molecule. This representation should be understandable by the computer. That means we can see through two-dimensional and three-dimensional representation, but computer sees it's an image. We need certain programs that should be understandable by computer, that is a molecule. And whether you are using classical mechanics or whether you are using quantum mechanics, you are going to need some sort of representation. Now there are different ways of representing a molecule for the computer, and this certain software are also required and involved in sketching of these molecules and to perform laborious calculations. For example, you can see the Marvin sketch, and we'll have a demo after this lecture also. The simplest representation of the molecule is external coordinate representation. Basically, it involves x, y and g coordinates and setting all these atoms just considered to be a point in space. Just these three coordinates x, y, g. So if every atom has three coordinates, if there are n atoms in a molecule, we require three different independent parameters to describe the molecule. For example, if you have a molecule and could specify all its bond lengths, bond angles and torsion angles, a collection of all these bond lengths, bond angles and torsion angles, it could specify the molecule. However, in this case, you need only 3n minus 6 parameters, translational and vibrational motions of the molecule, 3n minus 6. It represents, if you have n atoms, there are 6 missing parameters in the 3n minus 6 parameterization. And these parameters will specify the absolute positioning and the orientation of the molecule in the space. If a molecule is in front of you or wherever, it is the same molecule. If you take a benzene or ethylene, ethane, whatever it may be, if it is in front of you or wherever it is, the molecule is benzene or ethylene. So we do not really bother in many cases regarding its positioning and orientation. So in such cases, 3n minus 6, where the 6 parameters are missing, it is sufficient to represent the molecule. Let us say only the interactions between A and B molecules. All the 3n parameters for each molecule A and B is required. It will be required and you cannot ignore those 6 parameters. So comparing the two things, external coordinates as well as internal coordinates, external coordinates require 3n parameters because between A and B it requires external parameters. External coordinates require 3n parameters, but internal coordinates require 3n minus 6, where the 6 parameters missing. The external coordinates are very sensitive and orientation of the molecule. If I take a molecule here and move it here without changing its conformation, in this case the external coordinates will change. This may be good sometimes or may not be good. Sometimes internal coordinates will not change unless there is a change of conformation and orientation and configuration of the molecule. So if specifically you are interested in conformation or configuration of the changes you are interested in, such cases sometimes internal parameters, nothing but internal coordinates, may be advantageous. However, if studying like more than one molecule that is in space, the way they interact, like in the case you seen between A and B, in that case external coordinates are better because internal coordinates only specify what is internal. It will not specify the relationship between two molecules, one molecule to another. Now let us see whether these two representations, nothing but external and internal, are equivalent or not. That means given a set of external coordinates, can we calculate the internal coordinates? Or given a set of internal coordinates, can we calculate the external coordinates? If it can, then it means then the two representations are absolutely equivalent. That means if the both can define each other, then these are two equal and absolutely equivalent. Let us see. Now let us take the bond length in external coordinates. For every bond length we have two atoms and coordinates. Let's call these coordinates as x1, y1 and g, and x2, y2, g2. The bond length in the case is nothing but the distance separating the two atoms. This is nothing but Euclidean distance. Euclidean distance is nothing but a true straight line distance between 2 points in space, and you can apply this Euclidean distance formula to get a bond length. This means as far as the bond length is concerned, with a given set of external coordinates, you can always calculate bond lengths. Now let's take this in the case of bond angles. For the bond angles for a given 3 atoms which are connected each other, we could define each of the bonds using vector representations, vectors A and B. In this case, the bond angle is between these two vectors and is given by the inverse cosine of the dot product. These two vectors, now the dot product is simple to calculate, and finding out the inverse cosine of this dot product is so easy. So given the external coordinates specified in the terms of x1, y1, g1, x1, y2, g2, x1, y3, g3. In this case, one can calculate the two vectors, and from these two vectors you can easily calculate the bond angle between them, which means again in this particular case external coordinates can be completely converted into internal coordinates. That means the relevant point angles. Now let's come to the torsional angles. Here the situation is a little bit more complex. To understand the torsional angle, we need 4 atoms. Those are connected in its chain. Now here we are seeing the 3 atoms in space. A plane is defined. Suppose we have 4 atoms, A, B, C and D. Atom A, B and C will define one plane. Similarly B, C and D. These two planes are coplanar, that is both of them may be embedded into a bigger plane or they need not to be embedded. If they are not embedded, then there is a certain angle between two planes and this is called torsional angle. Now this can also be calculated with the given external coordinates, just like in the case of bond angles. So we can go ahead and given these four atoms, let's define three vectors A, B and C. You can see it was given in the figure. And then we define three other vectors QA, QB and QC. You can see QA is the cross product of vector A and vector B, which means QA is perpendicular to the plane that is defined by atoms A, B and C. Similarly QB. QB is the cross product of vector C and B. That means QB is perpendicular to the plane defined by atoms B, C and D. Then the QC is the cross product of QA and QB, which means it's the perpendicular to both of these two perpendiculars. Given such a set of these vectors, we can calculate the torsion angle with the formula which is the inverse product of cosine of QA and QB. That is multiplied by the dot product of vector B and vector QC. You can see the dot product of the vector B and vector QC can only have two values, plus 1 and minus 1. So effectively, what gives you is the torsion angle with 3n minus 6 internal parameters. So from this we can say, when we go from external to internal, which is 3n to 3n minus 6, we can definitely convert it. If you move from internal to external, we require certain information. For a single molecule, the 6 parameters can be arbitrary. That means it is based upon random choice. But if there are more than one molecule, we should define the position of one molecule with respect to other. Then we will have to use that information to obtain the remaining 6 parameters. But it exists very standard general algorithms which always work to convert this 3n minus 6 parameters in internal coordinates to the corresponding 3n external coordinates. The most used algorithm is fourth atom fixing algorithm. This is the one of the things. External coordinates can be converted into internal coordinates, but in doing so, one information is lost in some of the applications, that is the absolute position and orientation, particularly when you work with a single molecule. This loss is unimportant in some of the applications, but in other applications it is important. Then we have to use external coordinates information, but given a situation, sometimes internal coordinates are easier to handle, sometimes external coordinates are easier to handle. We have to use in a particular situation. So one can freely move one to the other depending upon our requirement.